Certified GitOps Associate Study Notes. GitOps terminology. 1. Continuous. Continuous is intended to match the industry standard term. Reconciliation continues to happen, not that it must be instantaneous. In GitOps, continuous refers to the ongoing, real-time process of monitoring and synchronizing the actual state of the system with the desired state as defined in the Git repository. Continuous reconciliation ensures that any changes, whether intended or accidental, are detected and resolved. Unlike traditional CI/CD pipelines that are event-driven, GitOps uses continuous reconciliation loops. This means that if any drift occurs between the desired state, defined in Git, and the actual state, running in the environment, the system will autonomously recognize the drift and attempt to correct it. The system stays perpetually in sync with the desired state without manual intervention, enabling self-healing mechanisms. 2. Declarative description. A configuration that describes the desired operating state of a system without specifying procedures for how that state will be achieved. This separates configuration, the desired state, from the implementation, commands, API calls, scripts, etc., used to achieve that state. GitOps relies on declarative descriptions of infrastructure and application states, as opposed to imperative approaches. A declarative model specifies what the desired state should be, rather than how to achieve that state. This contrasts with traditional systems where detailed procedures and scripts specify exact steps to modify infrastructure or deploy applications. In a GitOps environment, you define the end state in configuration files, and the system, via tools like Kubernetes or Terraform, automatically implements the necessary steps to achieve it. Common examples of declarative descriptions include Kubernetes manifests, YAML, Helm charts, and Terraform configurations. The declarative approach reduces complexity and allows infrastructure to be consistently reproduced. 3. Desired state. The aggregate of all configuration data that is sufficient to recreate the system so that instances of the system are behaviorally indistinguishable. This configuration data generally does not include persistent application data, for example, database contents, though often does include credentials for accessing that data, or configuration for data recovery tools running on that system. The desired state represents the target configuration or the exact way you want your system to look and operate. In GitOps, the desired state is stored in Git repositories, which act as the single source of truth for infrastructure, applications, and configuration management. This state includes details such as the number of application replicas, service configurations, network policies, and other infrastructure components. GitOps controllers like Flux or Argo CD monitor the live system against this desired state and work to ensure that the system is always aligned with it. Any changes to the desired state, such as infrastructure scaling or software updates, are made by committing to the Git repository, where they are automatically applied to the system. 4. State drift. When a system's actual state has moved or is in the process of moving away from the desired state, this is often referred to as drift. State drift occurs when the live state of a system differs from the desired state as defined in the Git repository. This can happen due to manual interventions, like a developer manually changing a Kubernetes configuration using kubectl, external factors, such as a server crashing, or unexpected system behavior. Drift is problematic because it can lead to inconsistencies, bugs, security vulnerabilities, and unpredictable system behavior. GitOps tools continuously check for drift and automatically correct it by applying the desired configuration from Git, ensuring that the live environment always reflects the desired configuration. 5. State reconciliation. The process of ensuring the actual state of a system matches its desired state. Contrary to traditional CI/CD, where automation is generally driven by preset triggers, in GitOps reconciliation is triggered whenever there is a divergence. Divergence could be due to the actual state unintentionally drifting from the desired state declarations, or a new desired state declaration version having been changed intentionally. Actions are taken based on policies around feedback from the system and previous reconciliation attempts, in order to reduce deviation over time. State reconciliation is the process by which GitOps systems like Argo CD or Flux compare the current state of a system, for example, applications running in Kubernetes, with the desired state stored in a Git repository. If differences or drift are detected, the system performs reconciliation to bring the actual state back into alignment with the desired state. This is done by updating, modifying, or deleting resources in the system to match the configurations in Git. Reconciliation is a core feature of GitOps, ensuring that systems are self-healing and automatically adjust to any discrepancies without manual intervention. 6. GitOps Managed Software System. A software system managed by GitOps includes one or more runtime environments consisting of resources under management, the management agents within each runtime, policies for controlling access and management of repositories, deployments, runtimes. A GitOps managed software system is an environment in which Git is the source of truth for all configurations and changes. It encompasses infrastructure, applications, networking, security policies, and other operational aspects that are managed through Git. Changes to the system are made by modifying the Git repository, which triggers automated deployment or infrastructure provisioning processes. Software systems managed by GitOps typically leverage tools like Kubernetes for container orchestration, Terraform for infrastructure as code, and other GitOps controllers to maintain the desired state of the system. This approach ensures that systems are auditable, version-controlled, and consistent across multiple environments, such as development, staging, and production. 7. State Store. A system for storing immutable versions of desired state declarations. This state store should provide access control and auditing on the changes to the desired state. Git, from which GitOps derives its name, is the canonical example used as this state store, but any other system that meets these criteria may be used. In all cases, these state stores must be properly configured and precautions must be taken to comply with requirements set out in the GitOps principles. The state store in GitOps is where the desired state of the system is stored and versioned. Git repositories are the most common state stores, but other options like OCI, Open Container Initiative, registries can also serve as state stores. The state store must support versioning, immutability, and auditing, ensuring that changes to the desired state are traceable and reversible. Git provides these capabilities by allowing commits, branches, and tags to represent different versions of the system's configuration. In some cases, like using OCI registries, configurations are stored as container images or artifacts that can be pulled and applied to a system. The state store ensures that any rollback or recovery operation is straightforward and reliable. 8. Feedback loop. OpenGitOps follows control theory and operates in a closed loop. In control theory, feedback represents how previous attempts to apply a desired state have affected the actual state. For example, if the desired state requires more resources than exist in a system, the software agent may make attempts to add resources, to automatically roll back to a previous version, or to send alerts to human operators. GitOps is designed as a closed-loop control system, where changes to the system are automatically reconciled and verified. The feedback loop starts with a change to the Git repository, triggering the system to synchronize the live state with the new desired state. Internal observability tools continuously monitor the system for drift and report back any differences between the actual and desired states. This feedback is used to adjust and correct the live environment as needed. Additionally, external observability systems can be integrated to notify operators of state changes, deployment issues, or synchronization failures. The feedback loop ensures that the system remains consistent, predictable, and compliant with its desired configuration. 9. Rollback. Rollback is the process of reverting a system to a previous state. In GitOps, the rollback process is often automated by changing the desired state to a previous version and allowing the reconciliation process to apply that state. Git revert is an example of a rollback operation in Git. One of the key benefits of GitOps is its inherent support for rollbacks. Since all configurations are version controlled in Git, reverting to a previous state is as simple as reverting a Git commit. When a system encounters issues, operators can quickly roll back to a stable state by applying the previous configuration from the Git history. This makes it easy to recover from failed deployments, misconfigurations, or security incidents. Rollbacks in GitOps are reliable because they leverage the full power of Git's history and version control, ensuring that previous configurations can be quickly and accurately restored without having to manually reverse changes. GitOps Principles. GitOps is a set of principles for operating and managing software systems. These principles are derived from modern software operations but are also rooted in pre-existing and widely adopted best practices. The desired state of a GitOps managed system must be declarative. A system managed by GitOps must have its desired state expressed declaratively. Versioned and immutable. Desired state is stored in a way that enforces immutability, versioning and retains a complete version history. Pulled automatically. Software agents automatically pull the desired state declarations from the source. Continuously reconciled. Software agents continuously observe actual system state and attempt to apply the desired state. 1. Declarative. The declarative principle in GitOps means that all system configurations, infrastructure, and application states are defined in a declarative manner. This contrasts with imperative approaches, where specific instructions are provided for how to achieve a desired state. In a declarative model, you specify what the end state should be, not how to reach it. For example, in Kubernetes, you might use YAML files to describe the desired number of replicas for a deployment, or the configuration of a service. Tools like Kubernetes, Terraform, or Helm then interpret and implement those declarations to ensure the system matches the desired state. By embracing declarative configurations, GitOps makes it easier to manage complex systems. This is because you focus on describing the ideal outcome rather than writing procedural scripts. Additionally, this approach makes systems more resilient and easier to replicate. For instance, if a system goes down, the declarative files stored in Git can easily recreate it from scratch. Key benefits. Clarity, describing what the system should look like eliminates ambiguity. Consistency, all environments, dev, staging, production, can follow the same declarative instructions, minimizing configuration drift. Simplicity, DevOps teams don't need to worry about the how, they just describe the desired end result, and GitOps controllers handle the rest. 2. Versioned and immutable. In GitOps, every desired state is versioned and immutable. This means that all configurations and system states are stored in a version control system, typically Git, which acts as the single source of truth. Every change to the desired state of a system, whether for infrastructure or applications, is captured in a Git commit, which is timestamped, can be audited, and is fully traceable. Versioning ensures that you can track every change made to the system. You have a complete history of system state over time, making it easy to audit changes, investigate bugs, and analyze past configurations. You can revert to previous configurations quickly through Git's rollback capabilities. Immutability in this context means that once a version is committed to Git, it is unchangeable. If you need to modify the system's desired state, you create a new commit with updated configurations. This ensures that every version of your system is locked in time, eliminating the risks of tampering or unintended changes. Using versioned and immutable states in GitOps provides auditing. Git provides a complete audit trail, which is essential for regulatory compliance and security. Accountability. Each change can be attributed to a specific user or process, improving transparency and accountability. Rollback and recovery. If an issue arises, teams can easily roll back to a previous, stable version without needing to manually undo changes. 3. Pulled automatically. In the GitOps model, configurations and system states are pulled automatically by agents or controllers running in your environment. This contrasts with traditional CI/CD models where changes are often pushed from a pipeline into the system. In a GitOps setup, controllers such as Argo CD or Flux continuously monitor the Git repository for any changes in the desired state. When a new change is committed to the repository, these agents automatically pull the updated configuration and apply it to the system, ensuring that the live system reflects the latest desired state. Advantages of the pull approach. Security. By having the system pull configurations from Git, you reduce the risk of unauthorized push operations directly into production environments. This adds an extra layer of security. Self-sufficiency. Systems become more autonomous as they monitor and sync themselves with the desired state from the repository. This reduces the need for manual intervention. Consistency. Multiple environments, for example, dev, staging, prod, can pull from the same repository, ensuring that they are all synchronized with the same configurations. In essence, the pull mechanism aligns with the GitOps philosophy of automation and continuous synchronization between the desired state, stored in Git, and the actual state, running in the cluster. 4. Continuously reconciled. The principle of continuous reconciliation is central to GitOps and is what ensures that systems remain in sync with the desired state over time. GitOps controllers like Argo CD and Flux continuously monitor the current state of the system, comparing it with the desired state defined in Git. If any drift is detected, such as manual changes to infrastructure or unexpected failures, the GitOps controller identifies this mismatch and takes corrective action by reconciling the actual state with the desired state. This continuous reconciliation loop ensures that the system is always aligned with the configurations stored in Git. How it works. The controller frequently checks the live system against the desired configuration in the repository. If there's a divergence, the system attempts to correct it, either by reapplying the desired configuration or notifying the team of the issue. If the system drifts again, the process is repeated until the actual state matches the desired state. Benefits of continuous reconciliation. Self-healing. Systems automatically heal themselves by correcting any deviations from the desired state. Reliability. There's no need to worry about whether the system is running in the correct state. It will always converge towards the desired state stored in Git. Error prevention. Unwanted manual changes, configuration drifts, or system failures are caught and corrected almost immediately, preventing them from causing bigger issues in production. This principle makes GitOps particularly powerful for environments like Kubernetes, where configurations can change frequently and maintaining consistency is critical. Related practices. 1. Configuration as code. CAC configuration as code. CAC involves managing and provisioning infrastructure through machine-readable definition files, rather than physical hardware configuration or interactive configuration tools. This practice enables developers and IT operations teams to automatically manage and provision their infrastructure using code. CAC is a key component of GitOps, as it allows for the desired state of infrastructure to be described declaratively and managed alongside application code. Configuration as code, CAC, is the practice of managing and automating software configurations using code. Instead of manually configuring systems, applications, or infrastructure, all configurations are defined in code, typically in human-readable formats like YAML or JSON. These configuration files are stored in a version control system, like Git, and applied programmatically to systems. In GitOps, CAC plays a key role because all system configurations, whether for infrastructure, applications, or Kubernetes resources, are stored in Git and treated as code. This allows teams to manage configurations consistently, track changes, and easily revert to previous versions if necessary. Advantages of CAC. Consistency. By defining configurations in code, you ensure that environments remain consistent across deployments. Version control, like source code, configuration files are versioned, allowing you to track changes, audit configurations, and revert if needed. Automation, configuration changes can be automatically applied using tools like Kubernetes or Terraform, ensuring that environments are always up to date without manual intervention. Example in practice. A Kubernetes deployment YAML file is an example of CAC. It defines how a containerized application should be deployed, including the number of replicas, ports, and resource limits. CAC reduces human error by removing the need for manual configuration changes and helps with scalability, as configurations can be easily applied across multiple environments with minimal effort. 2. Infrastructure as code. IAC Infrastructure as code, IAC, is a key practice within DevOps that involves managing and provisioning computing infrastructure through code instead of through manual processes. With IAC, infrastructure is provisioned and managed using code and software development techniques, such as version control and continuous integration. IAC is fundamental to GitOps, enabling the automatic, consistent deployment of infrastructure alongside applications. Infrastructure as code, IAC, is a practice that applies the principles of code management to infrastructure. Instead of manually provisioning and configuring infrastructure, servers, networks, storage, IAC enables teams to define and manage infrastructure using code. Like CAC, these infrastructure definitions are typically written in human-readable formats, for example, YAML, HCL for Terraform, and stored in version control systems like Git. In GitOps, IAC is fundamental because infrastructure resources, such as virtual machines, containers, or cloud services, are provisioned and managed automatically based on the desired state defined in Git. This approach allows teams to manage infrastructure in the same way they manage software, using version control, code reviews, and automated deployments. Advantages of IAC. Automation. Infrastructure can be provisioned automatically and consistently across different environments, for example, dev, staging, prod. Repeatability. The same infrastructure setup can be reused and applied to different environments or projects, reducing the risk of configuration drift. Disaster recovery. IAC allows teams to recreate infrastructure from scratch in case of a failure, simply by applying the saved configuration files. Example in practice. Tools like Terraform or AWS CloudFormation allow teams to define cloud resources, EC2 instances, S3 buckets, VPCs in code and automate their deployment. IAC integrates seamlessly with GitOps practices, as the desired infrastructure state is stored in Git, monitored for changes, and automatically applied to the live environment by the GitOps controller. 3. DevOps and DevSecOps. DevOps and DevSecOps. DevOps is a set of practices that combines software development, dev, and IT operations, ops, to shorten the development lifecycle and provide continuous delivery with high software quality. GitOps can be seen as an evolution of DevOps principles, focused on using Git as a single source of truth for declarative infrastructure and applications. DevSecOps extends DevOps by integrating security practices into the DevOps process, ensuring that security is built into the software development lifecycle. GitOps can be used to enforce security policies and best practices across the software development lifecycle. DevOps is a set of practices that combine software development, dev, and IT operations, ops, to shorten the development lifecycle and deliver high-quality software faster. The goal of DevOps is to increase collaboration between development and operations teams, automate processes, and ensure continuous delivery of software to production environments. DevSecOps extends DevOps by integrating security into the DevOps pipeline. Instead of security being a separate process that happens after development and before production, DevSecOps ensures that security checks are integrated throughout the development lifecycle, from code writing to deployment. In GitOps, both DevOps and DevSecOps are important because GitOps inherently focuses on automation, collaboration, and continuous deployment. Git becomes the central hub for managing infrastructure and application states, enabling developers to make changes with minimal operations or security overhead. Advantages of DevOps/DevSecOps in GitOps, continued. Automation. GitOps automates the deployment process, allowing teams to continuously deliver updates to production without manual intervention. DevOps principles drive the use of automation in this process. Collaboration. Developers, operations, and security teams work collaboratively in GitOps environments. Changes to code or infrastructure are visible in Git repositories, where all team members can track, review, and approve updates. Security by design. With DevSecOps, security checks such as static analysis, vulnerability scans, and policy enforcement can be integrated into the CI/CD pipeline. This ensures that all code and infrastructure changes are secure before they are applied to production. Faster feedback loops. By integrating development, operations, and security workflows, GitOps allows for faster feedback loops. Any issues, such as security vulnerabilities or infrastructure misconfigurations, are identified early in the pipeline, reducing risks in production. Example in practice. A CI/CD pipeline that integrates security tools, like Snyk or Aqua Security, to scan code and container images for vulnerabilities during the build and deployment stages is an example of DevSecOps in action. In a GitOps environment, the security policies defined in Git are automatically enforced during the deployment process. By embedding security directly into DevOps practices, DevSecOps ensures that all applications and infrastructure changes deployed via GitOps meet security standards. 4. Continuous integration, CI, and continuous delivery, CD. Continuous integration, CI, the automated process of integrating code changes from multiple contributors into a shared repository. This process includes automated testing to validate code changes before they are merged, ensuring that the codebase remains stable and functional. Continuous integration, CI, is the practice of automatically building and testing code every time a developer commits changes to a source code repository, such as Git. CI ensures that code is integrated regularly and tested automatically, preventing integration issues and allowing teams to detect problems early in the development process. Continuous delivery, CD, the practice of automating the software delivery process to ensure that code changes can be deployed to production at any time. GitOps can be used to automate the continuous delivery process, ensuring that the desired state of the system is always reflected in the production environment. Continuous delivery, CD, takes this one step further by automating the deployment of code to production, or pre-production, environments once it passes all tests. In a CD pipeline, deployment is automated, and the system is always ready to release code to production at any time. Continuous deployment, a subset of CD, goes further by automating the release of code to production without requiring manual approval. In this case, any passing build is automatically deployed. In GitOps, CI/CD workflows are essential components. CI ensures that every code or configuration change is tested before it's integrated into the main branch. CD ensures that the state of the infrastructure or application defined in Git is automatically deployed to production as part of the GitOps process. Advantages of CI/CD in GitOps. Automation and speed. GitOps accelerates the deployment process by using Git to trigger automated deployment pipelines. Once a pull request is merged into the repository, the GitOps controller automatically applies the desired state to the cluster. Improved quality. CI/CD pipelines enforce testing at every step of the process. This helps catch errors early and ensures that only verified changes make it into production. Scalability. CI/CD pipelines can handle large-scale deployments by automating processes and ensuring consistent configuration across multiple environments. Example in practice. A A CI/CD pipeline in GitLab or Jenkins can automatically build, test, and deploy a new version of an application after a pull request is merged. The pipeline uses the GitOps controller to reconcile the current state of the Kubernetes cluster with the desired state in the Git repository. In a GitOps environment, the combination of CI and CD creates a fully automated and resilient deployment process, ensuring that applications are continuously integrated, delivered, and deployed with minimal downtime or manual intervention. These related practices, configuration as code, CAC, infrastructure as code, IAC, DevOps/DevSecOps, and CI/CD, work in conjunction with GitOps principles to create a streamlined, automated, and secure software development and operations lifecycle. They enable teams to manage everything from infrastructure to applications declaratively, version everything in Git, and automate deployment and rollback processes. GitOps patterns. GitOps patterns provide structured approaches to deploying, managing, and evolving applications and infrastructure in a GitOps-based environment. These patterns guide how teams handle application delivery, release management, infrastructure configuration, and system reconciliation, ensuring reliability and flexibility. Deployment and release patterns. Recreate. This pattern involves tearing down the existing instances of an application before deploying the new version. While straightforward, the main drawback is the downtime between stopping the old version and starting the new version, making it less desirable for production environments that require high availability. Rolling updates. Kubernetes supports rolling updates natively, allowing updates to be applied incrementally without taking the service down. This strategy updates pods one by one, ensuring that a certain number of old and new pods are running simultaneously, which minimizes downtime and ensures that at least part of the application remains available during the update. Blue-green involves running two identical environments, blue for the current version and green for the new version, and switching traffic from blue to green once the new version is verified to be stable. This pattern is useful for minimizing downtime and risk during deployments. 1. Deployment and release patterns. Deployment and release patterns in GitOps refer to strategies used to push changes from development to production environments. These patterns include various methods for controlling how updates are applied to ensure stability and reliability. Blue/green deployments. This pattern uses two environments, blue, current production, and green, new version, for rolling out updates. The new version is deployed to the green environment, and once validated, traffic is switched over from blue to green. If any issues arise, traffic can easily revert to blue. This pattern involves deploying the new version alongside the old version in such a way that the new version processes real-world traffic in parallel without affecting the end-user experience, primarily for testing purposes. Canary releases. In this pattern, a new version of an application is rolled out incrementally to a small subset of users. This allows teams to validate the new version with real traffic before scaling it up to all users. If problems are detected, the deployment can be halted or rolled back. This involves rolling out the change to a small subset of users or servers first, monitoring the performance and stability, and then gradually increasing the rollout to more users. Rolling updates. This deployment pattern incrementally updates instances of an application without downtime. Each instance is replaced by the new version one at a time, ensuring that the application remains available throughout the update. Rollback. GitOps provides a natural rollback mechanism because all states are version controlled in Git. If an issue arises in production, the team can simply revert to a previous version in Git, and the GitOps controller will restore the cluster to the earlier state. Advantages. Minimizes downtime. Blue/green and canary releases ensure that any issues with new versions do not impact the entire user base. Easy rollbacks. Since the entire infrastructure and application state is stored in Git, rolling back to a stable version is as easy as reverting to a previous commit. Automated and predictable. With deployment patterns in GitOps, the process is automated and follows a predictable series of steps defined by Git, ensuring consistency across environments. 2. Progressive delivery patterns. Progressive delivery patterns are strategies for incrementally releasing updates, ensuring that only a small percentage of users are exposed to a change initially. These patterns aim to minimize risks and allow for a phased rollout of features. Canary deployments, as described earlier, this pattern involves deploying the new version to a small group of users first. If no issues are detected, the deployment continues to progressively roll out to more users. A/B testing. This pattern allows 2 or more versions of an application to run simultaneously, each exposed to a subset of users. Based on performance or user feedback, the better performing version can be rolled out to the full user base. Similar to Canary releases, but focuses more on comparing user behavior between the old and new versions to make data-driven decisions on feature adoption. Feature flags. In this pattern, features are toggled on or off at runtime, allowing teams to release new features behind a flag. This provides fine-grained control over which users see the new features and ensures easy rollbacks by toggling the feature off if necessary. Advantages. Reduced risk. By progressively rolling out updates, issues can be identified early and limited in scope before affecting all users. Granular control. Teams can control exactly which features or versions users are exposed to, enabling experimentation and validation without impacting production stability. Rapid rollback. With feature flags, rolling back a change is instantaneous by toggling the flag without needing to redeploy. 3. Pull versus event-driven approaches. Pull versus event-driven. Principle 3 specifies the desired state must be pulled rather than pushed, primarily because the software agents must be able to access the desired state from the state store at any time, not only when there is an intentional change in the state store triggering a push event. This is a prerequisite for reconciliation to happen continuously, as specified in Principle 4. Note that, in contrast to traditional CI/CD, where automation is generally driven by preset triggers, in GitOps, reconciliation is triggered whenever there is a divergence. Divergence could be due to the actual state unintentionally drifting from the desired state declarations, not only due to a new desired state declaration version having been changed intentionally. Pull-based, required for GitOps, agents within the cluster continuously monitor the Git repository for changes and apply updates automatically. Event-driven, while not the primary model in GitOps, event-driven mechanisms can complement GitOps by triggering actions based on specific events. The GitOps model supports 2 primary approaches to synchronize the actual state of the system with the desired state: pull-based and event-driven reconciliation. Pull-based model. In a pull-based GitOps setup, agents, like Argo CD or Flux, continuously poll the Git repository to detect changes in the desired state. When a change is detected, the agent pulls the updated configuration and applies it to the Kubernetes cluster. Advantages. Self-healing. If the cluster state drifts from the desired state, the agent will automatically pull the correct configuration and apply it. Security. Since the cluster pulls the configuration from Git, no external service needs access to modify the cluster, minimizing the attack surface. Event-driven model. In an event-driven GitOps system, a change in the Git repository triggers an event, such as a webhook, which pushes the updated configuration to the cluster. This model allows for more immediate reconciliation but requires more setup. Advantages. Faster response. Event-driven reconciliation can respond to changes in real time, applying updates faster than polling-based systems. More control. You can configure the triggers to initiate reconciliation only under specific conditions, allowing for more fine-tuned deployment workflows. Example in practice, a team using Argo CD with a pull-based model would see the agent constantly checking for new commits in the repository and applying them to the cluster, whereas an event-driven approach might use a Git webhook to immediately notify the cluster of updates. 4. Architecture patterns. Architecture patterns, in cluster and external reconciler, state store management, etc. In cluster reconciler, a software agent that runs within the cluster and is responsible for monitoring the state of the cluster and applying the desired state. External reconciler, similar to in-cluster reconcilers, but run outside the cluster, often used for multi-cluster management or for managing resources that are not directly accessible from within the cluster. State store management, structuring and managing the state store to ensure immutability, versioning, and complete version history. Secrets management, managing secrets in a secure and compliant manner, often using tools like Vault, Sealed Secrets, or GitOps-specific solutions like Cube. Secrets. GitOps supports different architectural patterns for implementing controllers and reconcilers that monitor and apply the desired state across infrastructure and applications. The choice of architecture pattern depends on factors such as security, scalability, and system complexity. In Cluster Reconciler. In this pattern, the GitOps controller, like Flux or Argo CD, is deployed inside the Kubernetes cluster it manages. The controller continuously reconciles the actual state of the cluster with the desired state in the Git repository. Advantages. Security. No external access is needed, as everything is managed within the cluster. Simple setup, the GitOps controller can directly interact with the Kubernetes API, making it easier to monitor and apply changes. External reconciler. Here, the controller is hosted outside the Kubernetes cluster and communicates with the cluster remotely to apply changes. This is useful when managing multiple clusters from a centralized control plane. Advantages. Centralized management. One external controller can manage multiple clusters, enabling easier multi-cluster deployments. Scalability. External reconcilers can scale independently of the clusters they manage, allowing for more complex or resource-intensive management tasks. State store management. In GitOps, the state store is where the desired state is stored. Typically, this is a Git repository, but other storage options like Ochi registries can also be used for storing container images or configuration bundles. The state store ensures immutability, versioning, and access control. Example, a team using Flux may store its configuration in a GitHub repository or an Ochi registry for storing Helm charts. The controller regularly checks the state store to ensure that the actual state of the cluster matches the desired state. Advantages of these patterns. Consistency. Both in cluster and external reconcilers ensure that the cluster state is always in sync with the state store, reducing drift and maintaining stability. Scalability. External reconcilers enable centralized control of multiple clusters, making it easier to manage at scale. Flexibility. Different state store options allow teams to choose the best storage solution for their needs, for example, Git for versioning or Ochi for image management. Summary. GitOps patterns, such as deployment and release strategies, progressive delivery techniques, pull versus event-driven architectures, and in-cluster versus external reconcilers, provide a structured approach to managing and evolving cloud-native applications and infrastructure. These patterns enable teams to automate deployments, control release processes, and ensure that the actual state of a system always matches the desired state stored in Git or other state stores. Tooling. Tooling in GitOps enables teams to manage, configure, and automate infrastructure and application deployment using various tools and formats. This includes defining the desired state, storing it, and utilizing reconciliation engines to ensure the system's actual state aligns with this desired state. Interoperability with notifications, observability, and CI tools enhances GitOps workflows by integrating essential development and operational functions. 1. Manifest format and packaging. Manifest format and packaging. Customize offers a template-free way to customize application configuration that simplifies the declaration of application manifests for Kubernetes. Helm provides packaging of Kubernetes applications into charts, making it easy to share and distribute a wide range of applications. Declarative YAML/JSON, a format for expressing the desired state of a system in a way that is both human-readable and machine-readable. GitOps relies on a declarative description of the desired state, typically stored in the form of manifests. These manifests describe how applications and infrastructure should be configured. Different tools and formats can be used for packaging and organizing these manifests to streamline deployment and versioning. YAML/JSON manifests. These are the most common formats for defining Kubernetes resources and infrastructure configurations. Simple YAML or JSON files describe the desired state of the application, including pods, services, and configurations. GitOps tools read these manifests and apply them to the cluster to create or update the required resources. Example, a Kubernetes deployment manifest in YAML that defines the number of replicas, container image, and other configurations. Helm charts. Helm is a packaging format that allows you to bundle multiple Kubernetes resources together in a reusable format. Helm charts enable you to manage complex applications with many interdependent components using templates and values files, allowing for more flexible and modular management of deployments. Advantages. Modularity. Helm allows teams to reuse charts across different environments, reducing redundancy. Parameterization. Charts can be parameterized, making it easy to apply the same configuration to multiple environments with slight variations. Customize. Customize is a tool for customizing Kubernetes YAML configurations. It allows you to create overlays for different environments without modifying the underlying base configurations, providing more flexibility and reuse in GitOps workflows. Advantages. Environment-specific overlays. You can define different overlays for development, staging, and production environments without duplicating the base configuration. Declarative. Customize natively supports Kubernetes manifests, making it a natural fit for GitOps. Carvel tools. Carvel tools like it provide configuration templating for Kubernetes, similar to Helm and Customize. They enable more powerful transformations and templating, allowing teams to dynamically generate and manage YAML files for Kubernetes resources. Advantages. Powerful templating. It supports logic and transformations within templates, providing more flexibility than standard YAML files. Consistent deployments. Carvel tools help maintain consistency across environments with declarative management. 2. State store systems. Git and alternative state store systems. Git and alternatives. Git, a distributed version control system that is widely used for source code management and is the canonical example of a state store used in GitOps. Ochi registry, a container registry that is used to store and distribute container images. S3, a scalable object storage service that is used to store and retrieve data. In GitOps, the state store is the system where the desired state of infrastructure and applications is defined and stored. The state store ensures that configurations are immutable, versioned, and easily accessible. While Git is the most common state store, other alternatives can also be used. Git is the default and most widely used state store system in GitOps. It serves as the single source of truth, where all configurations are stored in version-controlled repositories. Git allows teams to track changes, collaborate via pull requests, and roll back to previous states. Advantages. Version control. Every change is tracked, providing complete audit trail of modifications. Collaboration. Git branching and pull request features allow teams to collaborate on changes and ensure peer review before deployments. Rollback. If issues occur in production, rolling back to a previous stable version is as simple as reverting a commit. Ochi registry. An Ochi, Open Container Initiative, registry can be used as a state store for storing container images and application configurations. Tools like Flux support pulling state from Ochi registries, making them an alternative to Git repositories for storing application artifacts. Advantages. Scalability. Ochi registries are designed to scale with container images, making them ideal for large-scale deployments. Security. Ochi registries can sign and verify artifacts, adding an extra layer of security to the deployment process. Artifact repositories. In some GitOps setups, artifact repositories like JFrog Artifactory or Nexus can be used to store configuration files, packages, or container images. These repositories can act as the state store for deployments, especially in environments with large volumes of artifacts or complex dependencies. Advantages. Centralized storage. Artifact repositories provide a single location for managing all types of artifacts, including container images, Helm charts, and more. Versioning and retention. These repositories support artifact versioning and retention policies, ensuring traceability and control over what gets deployed. 3. Reconciliation engines. Argo CD, Flux, and alternatives. Reconciliation engines, Argo CD, Flux, and alternatives. Argo CD, a declarative, GitOps continuous delivery tool for Kubernetes. Flux, a tool for keeping Kubernetes clusters in sync with sources of configuration, like Git repositories, and automating updates to configuration when there is new code to deploy. Jenkins X, an open-source system that provides pipeline automation, GitOps, and continuous delivery for cloud-native applications on Kubernetes. Reconciliation engines are the core of GitOps, ensuring that the actual state of a system matches the desired state defined in the state store. These engines continuously monitor the configuration in the state store and apply any changes to the system. Argo CD. Argo CD is one of the most popular GitOps tools for Kubernetes. It acts as a reconciliation engine that monitors Git repositories and applies changes to Kubernetes clusters. Argo CD allows teams to define applications in Git, and it ensures that these applications are deployed and synchronized with the live environment. Key features. Declarative GitOps. Applications are defined declaratively in Git, and Argo CD ensures that the cluster state matches the desired state in Git. Visual interface. Argo CD provides a web-based UI that allows teams to visualize the synchronization status of their applications, see differences between live and desired states, and trigger manual syncs if needed. Multi-cluster management. Argo CD can manage multiple Kubernetes clusters from a single control plane, making it suitable for large-scale deployments. Flux. Flux is another powerful GitOps tool focused on continuous deployment. It continuously monitors a Git repository or OCI registry for changes in application configurations or container images and automatically updates the cluster to reflect these changes. Key features. Automated updates. Flux automatically applies changes from Git or OCI registries, ensuring that the cluster is always up to date with the desired configuration. Image automation. Flux can automatically update image versions in Kubernetes manifests when a new container image is pushed to a registry. Multi-tool integration. Flux works seamlessly with Helm, Customize, and other Kubernetes packaging tools, making it highly flexible. Other alternatives. Rancher Fleet. Fleet is a GitOps controller that simplifies multi-cluster management. It can manage Kubernetes clusters across hybrid and multi-cloud environments and uses a pull-based approach for GitOps. Jenkins X, a CI/CD solution built on Kubernetes. Jenkins X integrates GitOps principles by using repositories as the source of truth for application configuration and managing deployments using pull requests. Advantages of reconciliation engines. Automation. These tools continuously monitor and reconcile the cluster state, reducing manual intervention. Consistency. Reconciliation engines ensure that the actual state of the cluster always matches the desired state defined in Git, preventing configuration drift. Scalability. Tools like Argo CD and Flux can manage multiple clusters, making them suitable for large-scale GitOps deployments. 4. Interoperability with notifications, observability, and continuous integration tools. GitOps tooling is most effective when it integrates seamlessly with notifications, observability platforms, and CI systems. This allows teams to receive alerts, monitor deployments, and ensure continuous delivery without manual intervention. Interoperability with notifications, observability, and continuous integration tools. DORA metrics that are used to measure the performance of software delivery and operational processes, including deployment frequency, the frequency of deployments to production. Lead time for changes, the time it takes to go from code committed to code successfully running in production. Change failure rate, the percentage of changes that result in a failure in production. Time to restore service, the time it takes to restore service after a failure. Captain integrates with Flux and Argo CD to provide automated continuous delivery and operations for cloud-native applications. Prometheus and Alert Manager, used for monitoring and alerting, providing a rich set of metrics and alerting capabilities. Jenkins, a popular open-source automation server used to automate the building, testing, and deployment of software. Slack and Microsoft Teams, popular messaging platforms used for notifications and collaboration. Notifications, GitOps tools like Argo CD and Flux integrate with notification systems such as Slack, email, or webhooks to send alerts about synchronization events, deployment failures, or configuration drift. Notifications ensure that teams are informed in real time when critical events occur in the cluster. Example, in Argo CD, notifications can be set up to trigger on synchronization failures or when an application becomes out of sync, enabling faster incident response. Observability, integrating GitOps tools with observability platforms such as Prometheus, Grafana, or Datadog enables teams to monitor the health and performance of their applications and clusters. Observability ensures that the system's actual state is continuously measured and compared against the desired state. Example, Argo CD can export Prometheus metrics to track the synchronization status of applications, allowing teams to visualize deployment performance and detect anomalies. Continuous integration, C. GitOps workflows are closely tied to CI pipelines, as changes to infrastructure and application configurations often begin with code changes. Integrating GitOps tools with CI platforms such as Jenkins, Circle CI, or GitLab CI allows for seamless transitions between code commits, builds, and deployments. Example, when a developer commits a change to a Git repository, the CI pipeline can validate the change, run tests, and push it to production. The GitOps controller then applies the configuration to the cluster, ensuring the environment is always in sync with the codebase. Advantages of interoperability. End-to-end automation, CI/CD integration allows for a fully automated pipeline, from code commit to deployment, without manual intervention. Real-time feedback, notifications provide immediate insights into deployment issues, synchronization failures, or configuration drift. Visibility and monitoring, observability platforms help track the health of applications and clusters, ensuring that any discrepancies between the desired and actual state are detected and resolved quickly. Summary. GitOps tooling encompasses a range of technologies that facilitate declarative configuration management, automated synchronization, and seamless integration with critical operational tools. With various formats for packaging manifests, YAML, Helm, Customize, different state store systems, Git, Ochi, and powerful reconciliation engines, Argo CD, Flux, GitOps provides a scalable and reliable framework for managing cloud-native applications. The integration with notifications, observability, and CI tools enhances the entire GitOps process, ensuring that teams can operate efficiently, monitor system health, and react to changes in real time. CI/CD tools. Continuous integration/continuous deployment, CI/CD tools automate the process of building, testing, and deploying applications. These tools help streamline development, ensuring that code is integrated regularly, tested continuously, and deployed with minimal manual intervention. 1. Jenkins. Description: Jenkins is one of the most popular open-source automation servers for CI/CD pipelines. It supports thousands of plugins to automate various parts of the development lifecycle. Key features: highly customizable with plugins. Supports distributed builds on multiple nodes. Integrates with various source code management (SCM) systems like Git. 2. Circle CI. Description: Circle CI is a cloud-based CI/CD tool that automates builds, tests, and deployments. It provides a platform to build CI/CD pipelines that are easy to set up and scalable. Key features: provides ready-to-use Docker images for various languages. Deep integration with GitHub and Bitbucket. Supports parallel builds to speed up the development cycle. 3. GitLab CI. Description: GitLab CI is a built-in part of the GitLab platform, providing native CI/CD capabilities. It integrates directly with GitLab repositories, allowing for seamless automation of the development pipeline. Key features: single platform for repository hosting, CI/CD, and project management. Supports pipelines as code using YAML files, .gitlabc.ym. Powerful runner architecture for scaling across multiple environments. 4. Travis CI. Description: Travis CI is a cloud-based CI tool that integrates directly with GitHub to automatically test and deploy applications. It is known for its simplicity and ease of use. Key features: supports multiple programming languages like Ruby, Python, Go, and Node.js. Automatic builds for every pull request. Open source projects are free on Travis C. 5. Bamboo. Description: Bamboo is a CI/CD tool developed by Atlassian. It integrates with other Atlassian products like Jira and Bitbucket to provide end-to-end traceability of changes from code to deployment. Key features: built-in Git branching workflows. Out-of-the-box support for Docker and AWS code deploy. Deep integration with Atlassian Suite for better project management. 6. Team City. Description: developed by JetBrains, Team City is a CI/CD server that allows developers to run, monitor, and manage automated pipelines. It is highly flexible and integrates with many build, test, and deploy tools. Key features: pre-built Docker images to accelerate containerized workflows. Extensive support for various build runners and version control systems. Strong support for parallel execution and testing. 7. Azure DevOps. Description: Azure DevOps provides developer services for teams to plan work, collaborate on code development, and build and deploy applications. It offers integrated CI/CD pipelines in the cloud. Key features: integrates with Azure services for smooth cloud deployments. Can be used with any Git repository. Provides dashboards for pipeline monitoring and traceability. 8. GitHub Actions. Description: GitHub Actions is a CI/CD service within GitHub that allows developers to automate workflows. It integrates directly with GitHub repositories and allows users to define workflows with YAML files. Key features: fully integrated with GitHub repositories. Built-in support for automation and event-driven workflows. Can run builds and tests in different environments using Docker. Git Tools. Git Tools provide version control capabilities, allowing developers to track changes to their codebase, collaborate with other team members, and manage code versions across distributed teams. 1. Git. Description: Git is a free and open-source distributed version control system designed to handle everything from small to large projects efficiently. It tracks changes to files, enabling multiple developers to work on the same project simultaneously. Key features: supports branching and merging, making it easy to work on features and bug fixes concurrently. Local and distributed version control, allowing offline work. Strong support for collaboration and project history. 2. GitHub. Description: GitHub is a web-based platform that provides Git repository hosting and additional collaboration features. It offers code review, issue tracking, project management, and CI/CD features. Key features: integrates CI/CD using GitHub Actions. Provides pull requests for code review and branch merging. Social coding features like forks, stars, and discussions. 3. GitLab. Description: GitLab is a complete DevOps platform, offering Git-based repository hosting, CI/CD pipelines, project management, and more. It allows for managing the full software development lifecycle from a single platform. Key features: built-in CI/CD pipelines. Support for containerized deployments using Kubernetes. Project management features like issue boards and milestones. 4. Bitbucket. Description: Bitbucket is a Git-based source code repository platform that integrates with Atlassian's suite of products like Jira and Trello. It supports both Git and Mercurial repositories. Key features: powerful integration with Jira for issue tracking and project management. Bitbucket pipelines for CI/CD. Supports private repositories for free. 5. SourceTree. Description: SourceTree is a free Git client that provides a graphical interface for managing Git repositories. It simplifies Git operations like cloning, committing, branching, and merging for developers who prefer a visual tool. Key features: visual representation of Git branches and histories. Supports both Git and Mercurial. Makes it easier to handle pull requests and resolve merge conflicts. 6. Git Kraken. Description: Git Kraken is a Git GUI and issue tracking tool designed for developers and teams. It provides an intuitive interface for Git operations and integrates with GitHub, GitLab, Bitbucket, and other platforms. Key features: visual Git commit graph and history. Support for branching, merging, and rebasing. Integrates with popular issue trackers like Jira and Trello. 7. Git Cola. Description: Git Cola is a powerful yet simple GUI for Git. It is an open source, lightweight, and customizable Git client designed for simplicity and performance. Key features: simple interface with basic Git functionalities. Extensible with plugins. Open source and highly customizable. 8. Tortoise Git. Description: Tortoise Git is a Git client for Windows that integrates directly with the Windows File Explorer, making Git operations accessible through the right-click context menu. Key features: seamless integration with Windows Explorer. Supports all Git operations. Provides visual feedback for changes in the working directory. 9. Git Tower. Description: Git Tower is a commercial Git client that provides a simple graphical interface for working with Git repositories. It is widely used by both beginners and advanced Git users to manage their workflows. Key features: drag and drop Git operations. Git flow integration for simplified branch management. Conflict resolution tools for merging branches. Summary: CI/CD tools like Jenkins, GitLab CI, and Circle CI automate the software development lifecycle, from building to testing to deployment, ensuring faster and reliable delivery. Git tools like Git, GitHub, and GitLab help manage code versions, collaborate effectively across teams, and track changes efficiently. Together, these tools form the backbone of modern DevOps practices, enabling teams to ship high-quality software quickly and efficiently.
GitLab Certified Git Associate exam. GitLab organization structure. GitLab is a web-based DevOps lifecycle tool that provides a Git repository manager providing wiki, issue tracking, CI/CD pipeline features, and much more. Hierarchy. Groups, the highest level in GitLab structure, used to organize projects and users. Subgroups, nested groups within groups, allowing better organization of related projects. Projects, repositories that store code and resources for individual applications or services. Epics. Epics are large bodies of work that encompass multiple issues and can span projects and milestones. They help break down significant initiatives into smaller, manageable tasks. Epics can be nested within other epics, providing multi-level tracking. Useful for tracking progress on large features, organizational goals, or multiple related projects. Groups. Groups are collections of projects and users. A group can include multiple projects and serve as a way to manage permissions for multiple repositories at once. You can control member access at the group level, making it easier to manage permissions across multiple projects. Use cases. A group can represent a team, department, or product line. Subgroups. Subgroups are hierarchical layers within groups, allowing for more detailed organization. They enable Enable grouping projects by more specific criteria, such as by team, function, or feature. Example, a front-end group might have subgroups for React team and Vue team. Projects. A project in GitLab is essentially a repository that contains your code, issues, CI/CD pipelines, and other resources. Each project can be assigned members, have its own boards, milestones, and pipelines. Public and private projects can be created depending on access needs. Issues. Issues are GitLab's method of tracking tasks, bugs, and feature requests. Each issue can be assigned to a team member, labeled, prioritized, and linked to a specific milestone or board. Issue templates can be used to standardize issue creation across projects. Participants. Participants in GitLab refer to users involved in discussions or actions within an issue, merge request, or milestone. You can mention participants in comments by using the @ symbol followed by their username. Labels. Labels are used to categorize issues, merge requests, or epics. They provide a way to filter and organize work. Labels can be used to mark the status of an issue, for example, bug, enhancement, in progress, or indicate priority. Milestones. Milestones allow you to group issues and merge requests under a common goal or timeframe, often linked to a release. Progress can be tracked as a percentage of completed issues tied to the milestone. Boards. GitLab issue boards provide a Kanban-style view for tracking issues and merge requests. You can create columns for issues in different stages, such as to do, in progress, and done. Boards can be configured per project or group level. GitLab terms. Repository, where your project's files are stored, including code, documentation, and CI configuration. Pipeline, a set of steps that GitLab CI/CD runs on your project, such as build, test, and deploy. Merge request, GitLab's version of a pull request, allowing code to be reviewed and merged. Branch. A branch is a parallel version of your project's code. You can create multiple branches from the main branch to work on features or fixes independently. Common branches include main, or master, and development branches. Tag. Tags are specific points in Git history often used to mark releases. For example, v1.0.0. Tags are immutable, meaning they won't change and are useful for referring back to stable versions of the code. Checkout. Git checkout is a command used to switch between different branches or to restore files in your working directory. Merge. Merging is the process of integrating changes from one branch into another, typically from a feature branch into the main branch. GitLab allows for merge requests to handle this with peer review and CI checks before merging. Commit. A commit is a snapshot of your changes in the repository. Each commit records who made the changes, when, and the changes themselves. GitLab uses commits to track changes to files and logs them as part of the project history. Push. Push, the process of uploading commits from your local Git repository to a remote repository. For example, GitLab. Workspace. A workspace in GitLab is your working environment, including projects, pipelines, and other tools available for development. Git commands. Git init, initialize a new Git repository. Git add, stage files for commit. Git commit, save changes to the repository. Git push, push local changes to the remote repository. Git pull, fetch and integrate changes from the remote repository. Git merge, combine different branches. Git branch, manage branches in your repository. CI/CD. Continuous integration, C. Automatically testing your code after every commit to ensure new changes don't break the project. Continuous delivery, CD. Automating the deployment of tested code into production environments. .gitlabc.ym file. The GitlabC.ym file is the configuration file that defines your CI/CD pipeline. Each pipeline consists of jobs with different stages: build, test, deploy, and these stages are executed in sequence. GitLab Runner. GitLab Runner is the application that processes the jobs defined in GitLab CI. You can install GitLab Runner on a local machine, a server, or a container. SSH keys. SSH keys allow secure access to GitLab repositories. They are used to authenticate Git operations and secure communication between your machine and the GitLab server. Additional tools used for code review and collaboration. Merge requests, used for code reviews and merging changes into the main branch. Code snippets, share small, reusable blocks of code within a project or issue. Discussions, inline comments on code, useful for peer reviews. Snippets. Snippets in GitLab allow you to share small sections of code with others. They can be public or private and help reuse code efficiently across multiple projects or teams. Wikis. Wikis in GitLab provide a space to store and organize project documentation. Each project or group can have its own wiki for managing internal guides, processes, and knowledge sharing. Web IDE. GitLab Web IDE allows you to edit files directly within your browser. It's a fully integrated development environment where you can edit code, commit changes, and submit merge requests without leaving the GitLab interface. Docker. Docker is a platform used to package applications and their dependencies into lightweight containers. GitLab supports Docker integration for building, testing, and deploying applications within CI/CD pipelines. GitLab security scanning. GitLab includes several security tools to scan your codebase for vulnerabilities, such as SAST, Static Application Security Testing, DAST, Dynamic Application Security Testing. Container scanning analyzes Docker images for security vulnerabilities. GitLab SAST scanning. SAST, Static Application Security Testing, scans your codebase for vulnerabilities before it's deployed. It checks for security issues in your source code and dependencies. Results are shown in merge requests, allowing developers to address issues before merging their code into the main branch. This detailed breakdown should give you an in-depth understanding of each GitLab concept. Let me know if you'd like to explore any topic further. 4.0. You said they need to be more in-depth. ChatGPT said. ChatGPT. Absolutely. I'll dive deeper into each topic, elaborating on advanced features, use cases, and integration points in GitLab. Here's an even more detailed breakdown. GitLab organization structure. Hierarchy levels. Instance level. This is the topmost level that manages the entire GitLab environment. It's often used in self-hosted GitLab setups and controlled by system administrators. Groups represent a collection of related projects and users. Groups can be used to manage the roles and access controls for multiple projects. Subgroups provide additional hierarchical layers under a group, allowing complex organizations to separate teams, departments, or even features within one parent group. Subgroups can inherit permissions from their parent group, simplifying user management. Projects. These are individual repositories for your code. Each project can have its own CI/CD pipeline, issues, labels, and contributors, but project-level permissions can also be controlled by group membership. Advanced use case. Large enterprises use multiple subgroups under a group to separate projects by departments. For example, front-end development, back-end development, and infrastructure, but keep the overarching permissions inherited from the top-level group. Epics. Scope and purpose. Epics help break down significant business goals or large features into smaller, more manageable tasks. Each epic can contain multiple issues spanning multiple projects. Epics are hierarchical in nature, meaning an epic can have sub-epics. This allows you to build complex project plans where an overarching goal is divided into smaller goals, each tracked individually. Cross-project epics. Epics are not confined to a single project. They can include issues from different projects, which is critical for organizations that work on interrelated projects that must be coordinated. Advanced use case. An engineering team working on a large product feature, such as user authentication overhaul, would create an epic. Inside this epic, there would be issues for the UI/UX changes, backend changes, and security updates, each worked on by different teams and within different projects, but all tracked under one epic. Groups. Detailed permissions model. Groups allow granular control over project access. You can assign roles such as guest, reporter, developer, maintainer, and owner at the group level, controlling what actions each user can take. Groups also allow shared runners for CI/CD, container registries, and artifact repositories across projects. With app/SIM integration, in enterprise setups, groups can be synced with external identity providers like WordApp or SIM, ensuring that organizational roles automatically map to GitLab permissions. Advanced use case. In large enterprises, where multiple teams contribute to different services, groups make it easy to create a secure and manageable organization. For example, the security group might have access to every project in the company to run vulnerability scans, but not to modify code. Subgroups. Use cases. Subgroups enable further categorization within a group, helping organize projects by teams, client departments, or technologies. Inheritance. Subgroups can inherit the same permissions, pipelines, and CI configurations from their parent group. This can reduce administrative overhead and provide consistent security policies across a large enterprise. Advanced use case. A large tech firm may create a top-level group for their product team, then split the team into mobile, back-end, and front-end subgroups. Each of these subgroups may have additional subgroups for specific technologies, for example, Android and iOS in mobile. Projects. Advanced features. Merge requests. MR. GitLab projects rely heavily on MISRs for peer review and code collaboration. Each MISR can include reviewers, assignees, and automated checks, for example, linting or testing. CI/CD pipelines. Projects have integrated CI/CD pipelines defined in the GitLab CI file. Each project can have its own pipeline set up to run tests, build artifacts, deploy to production, or trigger external systems. Protected branches and tags. Projects can enforce branch protection rules to control who can merge or push code to specific branches, such as the main branch. Advanced use case. A project could include automation tools like Docker to package applications or run tests using CI/CD. For instance, a machine learning project may run data pre-processing pipelines and training models using GitLab CI features with GPU runners. Issues. Advanced features. Issue boards. GitLab supports issue boards, canned and style, that allow you to visually track the status of your issues across customizable columns. For example, to do, in progress, review, done. You can configure boards to automatically move issues based on their labels. Weight and priority. Issues can be weighted and assigned priority, which helps teams plan their workload and determine which issues to address first. Linked issues. GitLab allows issues to be linked to other issues or merge requests. This helps in tracking dependencies, i.e., one issue is blocked until another is completed. Advanced use case. In agile development, issues are used to track tasks, bug fixes, and user stories. They are often linked to MISRs, and issue boards can be used for sprint planning and tracking progress visually. Participants. Roles and permissions. Participants in issues or merge requests, MISRs, can play roles like assignee, reviewer, or commenter. They can actively take part in discussions, approvals, and code reviews. Participants are notified about any activity, comments, or updates in the issues/merge requests where they are involved. Advanced use case. For code reviews, Each Mr. is assigned a participant as a reviewer who must approve the changes. This ensures accountability and consistency across code quality. Labels. Advanced labeling. GitLab labels are customizable and color-coded to make it easy to filter and search issues or merge requests. You can set up scoped labels to limit labels to specific projects or groups. Label prioritization. You can assign labels such as priority:"high to issues that need immediate attention, or labels like feature and bug to classify work. Advanced use case. In a large development team, you can use labels for sprint planning, such as labeling issues with sprint:"week_1 and sprint:"week_2. GitLab also allows bulk labeling to categorize multiple issues at once. Milestones. Advanced tracking. Milestones in GitLab are useful for tracking progress toward a specific goal or feature release. They can include multiple issues and merge requests from different projects, which allows cross-project tracking. Milestone burndown charts. GitLab provides burndown charts that help track the progress of issues within a milestone, showing how many issues remain open. Advanced use case. A product team might create milestones for version 1.0 of their product, associating all the features, bugs, and tasks that need to be completed for that version. The milestone gives a comprehensive view of progress across various teams. Boards. Detailed configuration. Boards allow you to visually track the flow of work with customizable columns representing different stages in your development process. For example, backlog, in progress, code review, QA, done. Boards can be scoped to groups, projects, and even epics, giving teams flexibility in how they manage workflows. Advanced use case. Agile teams use boards to manage sprint tasks. Each board could have columns for the stages of the workflow, allowing team members to move issues across columns as they progress. GitLab terms. Repository. A repository contains your project's files, including code, documentation, and CI/CD configurations. Merge request. Mr. A Mr. is a request to merge code changes from one branch to another. It includes inline code reviews, discussions, and tests. CI/CD pipeline. A pipeline is a set of automated processes that GitLab CI/CD uses to build, test, and deploy your application. Advanced use case. GitLab pipelines are used to automate the release process. For instance, upon a successful Mr., a pipeline might automatically deploy code to a staging environment, run integration tests, and deploy to production. Branch. Branching strategies. GitLab supports several branching strategies, including Git flow and trunk-based development. In Git flow, there are long-lived branches, for example, main and develop, and short-lived feature branches. In trunk-based development, developers commit directly to the main branch, with small and frequent merges. Advanced use case. In a continuous delivery pipeline, a feature branch might be created for every new feature. After development and testing, this branch is merged into the develop branch for final integration before deployment. Tag. Advanced tagging. Tags are often used for marking stable versions or releases. GitLab allows lightweight tags, created locally, and annotated tags, which store additional metadata. Tags are helpful for software versioning, for example, v1.0, v2.1. Advanced use case. Before deploying to production, you might tag the last commit in your main branch as v1.0.0, creating a reference point for the code that can be easily accessed later. Checkout. Advanced use. Git checkout is used for switching branches or restoring files. It can also be used to inspect older versions of your project. You can use git checkout the new branch to create and switch to a new branch. Advanced use case. Developers use git checkout to switch between multiple feature branches and hotfix branches, ensuring isolated development. Merge. Merge conflict resolution. When two branches have conflicting changes, GitLab provides visual conflict resolution tools in the UI, guiding developers through resolving conflicts before merging. Fast-forward mergers versus three-way mergers. Fast-forward mergers only move the head of the branch forward, while three-way mergers create a new commit to combine changes. Advanced use case. In complex projects, conflicts may arise when multiple teams work on overlapping files. GitLab's conflict resolution interface helps mitigate such issues. Commit. Advanced concepts. Commits are snapshots of your project at specific points in time. Each commit has a SHA-1 hash, which uniquely identifies it. Best practices include writing meaningful commit messages, splitting large changes into multiple commits, and using squash commits to reduce the number of commits in misses. Advanced use case. A team might follow a conventional commit pattern, fix, chore, for better tracking of what each commit does, which can help automate versioning with tools like semantic release. Push. Git push. Git push updates the remote repository with commits made locally. You can push to different branches or even tags. GitLab allows integration with CI/CD pipelines to automatically trigger builds, tests, or deployments on every push to a branch. Advanced use case. When a developer pushes to the main branch, it can trigger an automatic build and deployment to a production environment, enabling rapid deployment workflows. Workspace. Definition. In GitLab, workspace refers to the developer's working environment, which includes repositories, pipelines, issues, users, and additional features like snippets and the web IDE. Each workspace is fully integrated with GitLab's tools, enabling smooth collaboration and development processes. Advanced use case. Developers can configure their workspace to automatically fetch the latest issues assigned to them or to display merge request updates as they happen. Git commands. Detailed overview. Git fetch downloads new data from the remote repository but does not integrate it with the local working directory. Git rebase allows integrating changes from one branch to another by replaying commits on top of the target branch. Git cherry pick. Apply the changes introduced by an existing commit to a different branch. Advanced use case. Developers use Git rebase to keep a feature branch up to date with the latest changes in the main branch before merging, maintaining a clean history. CI/CD. Advanced CI/CD features. GitLab CI/CD integrates deeply with Git repositories, allowing automatic testing, deployment, and monitoring of your applications. Triggers. You can define triggers to run pipelines on specific events, like when new code is pushed or a merge request is created. Artifacts. Each pipeline job can generate artifacts, for example, binaries, reports, that can be stored and shared between jobs or retained for future use. Environments. GitLab allows you to define environments like staging, testing, or production and associate them with specific pipeline stages. Advanced use case. A continuous deployment pipeline can be set up where, after passing all tests in the CI stage, a deployment job automatically pushes code to a production environment using Kubernetes. .gitlabc.ym file. In-depth breakdown. Stages. Define the different parts of the pipeline, for example, build, test, deploy. Jobs. The specific tasks that are executed in each stage. Each job can have different scripts, artifacts, and rules to determine when they should run. Variables. You can define environment variables at the job or pipeline level, which are used to configure the pipeline dynamically. Caching. To speed up jobs, cache commonly used dependencies or build artifacts, ensuring that jobs reuse them without downloading or generating them repeatedly. Advanced use case. In more complex pipelines, multiple environments, for example, dev, stage, prod, can be configured, and the pipeline can run different jobs for each based on the branch being pushed to. GitLab Runner. Advanced features. GitLab Runner is a lightweight agent used to run jobs specified in the gitlabc.ym file. Runner types. Shared runners, available to all projects in a GitLab instance. Specific runners, assigned to individual projects or groups. Auto-scaling. GitLab runners can be configured to auto-scale on cloud platforms like AWS or GCP to handle a large volume of jobs efficiently. Advanced use case. For large teams, GitLab can deploy runners in different environments. For example, dedicated build runners on AWS and testing runners on on-prem servers to speed up pipeline execution. SSH keys. Advanced use. SSH keys are used for secure communication between your machine and GitLab, allowing operations like cloning repositories, pulling code, and pushing commits without needing to re-enter credentials. SSH key types. GitLab supports both RSA and ED 25519 key pairs, with the latter being more secure. SSH keys can be linked to your GitLab profile for repository access or used in CI pipelines to access external systems. Advanced use case. You can set up deploy keys in GitLab, which allow a specific server or service to have read or write access to repositories securely, without needing user credentials. Additional tools used for code review and collaboration. Advanced code review. Inline code comments. During a code review and a merge request, users can add inline comments directly to specific lines of code. This is useful for pinpointing feedback or suggestions. Multiple approvals. GitLab supports requiring multiple approvers for merge requests, ensuring that code is reviewed by more than one person. CI integration. CI pipelines can be integrated with merge requests, allowing automatic tests to run and block merging if tests fail. Advanced use case. Large development teams often require automated code analysis. For example, SonarQube integration in merge requests, adding another layer of quality control. Snippets. Advanced features. GitLab snippets allow users to share small pieces of code, scripts, or configuration files with others. Snippets can be either public, internal, visible to logged-in users, or private. Snippets can be forked and commented on, making them useful for collaborative debugging or sharing solutions within the team. Advanced use case. You can use snippets to share deployment scripts with your team. A snippet could contain the necessary bash script for automating Kubernetes deployments. Wikis. Advanced features. Each GitLab project or group can have its own wiki to store documentation and internal guides. Wikis support Markdown for formatting, and version history allows tracking changes to documentation over time. GitLab wikis are ideal for internal knowledge sharing, providing documentation on how to set up projects, standards for code, and processes. Advanced use case. A DevOps team could maintain a centralized wiki within GitLab to document all infrastructure setup processes, best practices, and CI/CD pipeline instructions. Web IDE advanced features. GitLab's Web IDE provides a fully integrated development environment directly in the browser, where you can edit files, commit changes, create branches, and even submit merge requests. It offers live previews for changes. For web applications, an integration with the CI/CD system allows you to see pipeline results in the same interface. The Web IDE also supports Git operations, like stashing changes and pushing commits. Advanced use case. A quick bug fix or small edit to documentation can be done directly in the Web IDE without the need to clone the repository or use a local development environment. Docker. Docker integration with GitLab. Docker is a widely used platform for containerizing applications. In GitLab, Docker is often used in CI/CD pipelines to build, test, and deploy applications in a consistent environment. GitLab supports Docker runners, allowing jobs to be executed in isolated Docker containers. Container registry. GitLab provides a built-in container registry where you can store and manage your Docker images alongside your code. Advanced use case. In a microservices architecture, each service could be containerized and pushed to the GitLab container registry. The CI/CD pipeline could then deploy and run these services using Kubernetes. GitLab security scanning. Advanced security features. GitLab provides several built-in security tools, such as static application security testing, SAST, dependency scanning, and secret detection. These tools are integrated into the CI/CD pipeline, allowing security vulnerabilities to be detected early in the development process. Dynamic application security testing, DAST. This tool runs live security checks against running web applications, checking for common vulnerabilities like SQL injection or cross-site scripting, XSS. Advanced use case. A project can automatically run SAST scans after every merge request, and GitLab will flag any vulnerable code before it gets merged into production. GitLab SAST scanning. Detailed SAST overview. SAST scans the source code for known security vulnerabilities before it is compiled or executed. GitLab integrates this into CI/CD pipelines and reports issues found in the merge request view. Supported languages. GitLab SAST supports a wide variety of languages, including JavaScript, Python, Ruby, Java, Go, and more. Reporting. Results from SAST scans are shown in merge requests, allowing developers to address security issues before the code is merged. Advanced use case. A project using Node.js with dependencies could be automatically scanned for known vulnerabilities, and dependency updates can be flagged before going into production, ensuring the use of secure libraries.
GitHub Foundations. Domain 1, Introduction to Git and GitHub. Key concepts. Version control systems. Understand what a version control system, VCS, is and how Git, as a distributed VCS, differs from centralized systems, for example, Subversion, CVS. Key Git terms: repository, repo, commit, branch, merge, clone, pull, push, and fetch. Git versus GitHub. Git, a local tool for tracking changes in source code during development. GitHub, a cloud-based platform for hosting Git repositories, adding collaboration features like pull requests, issue tracking, etc. Basic Git commands. Git init, initialize a new Git repository. Git add, stage changes for the next commit. Git commit, commit stage changes. Git clone, copy an existing Git repository. Git status, view the current state of the working directory. Git log, show commit history. Git push/pull, push or pull changes to / from a remote repository. Repositories, local and remote. Understand the concept of local versus remote repositories. Basic repository management, for example, cloning, forking, and pushing code. Domain 2, working with GitHub repositories. Key concepts. Repository setup and structure. Creating a GitHub repository. Repository structure, README files, license files. Git ignore for ignoring files from version control. Setting up repository permissions, public versus private repositories. Managing files and directories. Adding, committing, and organizing files in a GitHub repository. Managing large files, for example, Git large file storage or Git LFS. Branches and merging. Branching, why and how to create branches, for example, feature, bug fix. Merging, how to merge changes from branches back into the main codebase and resolve conflicts. Domain 3, collaboration features. Key concepts. Forking and pull requests. Forking, creating your own copy of someone else's repository for development. Pull requests, proposing changes from your forked repository or branch into the original repository, often after a review. Code review process. Importance of code reviews in collaborative development. Using GitHub pull request reviews, assigning reviewers, commenting on code, approving or requesting changes. GitHub issues. Using issues to track bugs, enhancements, or tasks. Best practices for creating, assigning, and labeling issues. Closing issues via commits and pull requests. Collaboration tools. Project boards, using GitHub projects for task tracking, Kanban style. Discussions, a feature for team collaboration, brainstorming, and Q&A within a repository. GitHub Actions, CI/CD.
GitHub Actions, automate workflows like testing code, deploying applications, and more. Understand how to set up CI/CD pipelines using pre-built or custom workflows. Domain 4, Modern Development. Key concepts. Continuous integration/continuous delivery, CI/CD. Automating the build, test, and deployment process using GitHub Actions. Setting up automated testing with GitHub workflows. DevOps practices. Understand how GitHub fits into the DevOps lifecycle. Automating infrastructure deployments using GitHub, containers, and infrastructure as code, IAC, tools like Terraform. Integration with other tools. Integrating GitHub with other services like Jenkins, Travis C, or Circle CI for enhanced DevOps workflows. Domain 5, Project Management. Key concepts. GitHub projects. Organizing and managing your development tasks using project boards, for example, to do, in progress, done. Prioritizing issues and pull requests using projects. Milestones. Using milestones to track progress on larger goals or releases. Associating issues and pull requests with milestones. Labels. Categorizing and filtering tasks using labels, for example, bug, enhancement, documentation. Tracking progress. Linking issues and pull requests to projects for better visibility into the progress of a feature or task. Monitoring contributions and project health through GitHub Insights. Domain 6, Privacy, Security, and Administration. Key concepts. Repository permissions. Managing access control, for example, maintainers, collaborators, outside contributors. Understanding repository-level roles and permissions. Branch protection. Implementing branch protection rules, enforcing required status checks, requiring reviews before merging, etc. Security features. Using Dependabot to scan for vulnerable dependencies and automatically suggest updates. Security advisories, privately reporting and addressing security vulnerabilities. Secrets management, storing sensitive information like API keys securely in GitHub Secrets. Audit logs. Tracking and reviewing changes in your repository using GitHub's audit logs for organization admins. Domain 7, Benefits of the GitHub community. Key concepts. Open source contribution. The importance of contributing to open source projects on GitHub. How to find issues labeled with good first issue to help new contributors get involved. GitHub sponsors. Supporting open source developers through GitHub sponsors. GitHub discussions. Engaging in discussions and using them to collaborate on ideas, roadmaps, and general Q&A within a project. Networking and community engagement. Exploring ways to connect with other developers via GitHub communities, user groups, and events like GitHub Universe. GitHub education and learning. Accessing learning materials and certifications offered by GitHub for developers and teams, including educational resources for students. These study notes offer a high-level overview of each domain's key areas, allowing you to focus on critical aspects when preparing for an exam or mastering GitHub workflows. Let me know if you'd like to dive deeper into any particular topic. 4.0. You said. Expand greatly on each section. ChatGPT said. ChatGPT. Sure. Let's expand on each domain, providing more detailed explanations, concepts, and real-world examples to help you master each area. I'll break down key topics, important commands, and use cases for each section. Domain 1, Introduction to Git and GitHub. This domain introduces Git and GitHub, helping you grasp how version control works, why it's important, and how GitHub extends Git with collaboration features. Key concepts. Version control systems, VCS. Purpose, track changes in files and manage project versions over time. Essential for collaboration, versioning, and backup. Distributed versus centralized VCS. Centralized, systems like Subversion, SVN, store all versions on a central server, making it dependent on that server. Distributed, Git allows every user to have a full copy of the project's history, enabling offline work and reducing reliance on a central server. Advantages of Git. Speed, local copies allow for faster operations like committing, diffing, and checking logs. Flexibility supports nonlinear workflows, such as branching and merging. Collaboration, easy to share code and integrate contributions using GitHub. Git Basics. Repository, a collection of files that are tracked by Git. Repositories can be local, on your machine, or hosted remotely, on GitHub. Commit, a snapshot of changes. Each commit has a unique ID, SHA hash, and represents a specific state of your project. Branch, a parallel version of the project. Master/main is the default branch, but you can create others, for example, feature branches. Merge, incorporating changes from one branch into another. It combines the history of two branches. Basic Git workflow. Initialize a repository, Git init. This command creates a new Git repository in your project directory. Stage changes, Git add file. Moves changes into the staging area, preparing them for the next commit. Commit changes, Git commit m message. Commits the changes in the staging area to the repository with a descriptive message. Push to a remote repository, Git push origin branch. Uploads the local commits to the corresponding remote branch on GitHub. Clone a repository, Git clone less than URL greater than. Downloads a repository from GitHub to your local machine, making it possible to contribute. GitHub overview. GitHub versus Git. Git is a tool to track changes locally. GitHub provides cloud-based hosting for Git repositories and additional features like pull requests, project management, and integrations. Repositories on GitHub. Public repositories are visible to everyone, while private repositories are visible only to invited collaborators. Forks. Create a copy of someone else's repository to work on it independently. You can later request to merge your changes back into the original repository via pull request. Advanced Git concepts. Git configurations. Set your name and email for Git tracking. Git config global user.name your name. Git config global user.email you at example.com. Viewing logs and history. Use Git log to see a detailed commit history. You can limit it with options like Git log one line for a simpler view. Git aliases. Create shortcuts for common Git commands. Example, git config global alias.sd status will allow you to run git sd instead of git status. Domain 2, working with GitHub repositories. This domain focuses on how to create, manage, and organize repositories on GitHub. Key concepts. Creating repositories. You can create a new repository directly on GitHub by clicking New and following the prompts. You have the option to add a readme.md to explain the project's purpose. Add a git ignore to exclude files like environment variables or build artifacts from being tracked by Git. Choose a license, MIT, GPL, etc., for open source projects. Cloning a repository. Cloning a repository allows you to download it locally and make changes. Git clone repo URL greater than. Example, git clone https://github.com/user/repo.git. After cloning, you can push changes to the original repository if you have permission. Managing files in a repository. Committing files. After modifying files, use git add file to stage changes and git commit m message to commit them. Pushing to GitHub. After committing, push your changes to the remote repository using git push. Repository structure. readme.md, the main page of a GitHub repository. It typically includes a project description, installation instructions, and usage examples. License specifies the terms under which others can use and modify the code. .git ignore, a file listing patterns for files to exclude from version control, for example. Log, node_modules/. Branches. Branching allows for parallel development, such as developing a new feature or fixing a bug without affecting the main branch. Use git branch_name to create a new branch and git checkout branch_name to switch to it. Merging branches can be done with git merge branch_name, combining the changes into your current branch. Advanced repository management. Tags and releases. Tags mark specific points in history, such as software releases. Use git tag_name to create a tag and git push tags to push them to GitHub. Working with large files. GitLFS, large file storage, helps manage large files, like media assets, in a repository without bloating it. Use GitLFS track file to track large files. Domain 3, collaboration features. This domain is heavily focused on the collaborative features that GitHub offers, making it easier for teams to work together. Key concepts: forking and pull requests. Forking. A fork is your personal copy of someone else's repository. It allows you to experiment and develop features independently from the original repository. You can make changes and later submit those changes to the original repository via a pull request. Pull requests, PRs. A pull request is how you propose changes from your fork or a branch to the main repository. A PR provides a way to discuss changes with the project maintainers, perform code reviews, and run tests before merging. Code reviews. Code reviews are an essential part of the PR process. Reviewers provide feedback on code quality, design, and best practices. GitHub review features. Reviewers can comment on specific lines of code, approve the PR, request changes, or reject the PR. Use draft pull requests for work in progress, WIP, code, letting reviewers know that it's not ready for merging yet. Issues. GitHub issues are a way to track bugs, feature requests, and tasks. You can assign issues to collaborators, add labels for categorization, and set milestones for project goals. Issues can be closed automatically by mentioning fixes #issue_number in a commit message. Project boards. GitHub Projects is a built-in Kanban-style board for tracking issues, pull requests, and tasks. You can create columns like To Do, In Progress, and Done to visualize your team's progress. Integrate with issues and pull requests by linking them to the project board. GitHub Actions. GitHub Actions is an automation platform that allows you to define custom workflows for CI/CD, continuous integration/continuous deployment. Workflows are defined in YAML files in the GitHub/workflows/directory. Examples: running tests on every PR, deploying code to production after a merge. Collaborating with branches. Teams often use a branching model like Git Flow. Feature branches, short-lived branches for individual features. Develop branch, integrates features before being merged into the main branch. Release branches, used to prepare for production releases. Domain 4, modern development. This domain focuses on the tools and techniques used in modern software development, such as CI/CD, DevOps practices, and integration with other services. Key concepts: continuous integration/continuous deployment, CI/CD. CI, automatically testing your code after every commit to ensure that new changes do not break existing functionality. CD, automating the deployment process so that changes can be delivered to production faster and more reliably. GitHub Actions provides a framework for defining CI/CD pipelines. Example: automatically running tests on every pull request and deploying to staging after merging to the main branch. DevOps integration. DevOps is a set of practices that combines software development and IT operations to shorten the system development lifecycle. GitHub can integrate with various DevOps tools to facilitate infrastructure as code, IAC, managing infrastructure with code using tools like Terraform, Ansible, etc. Containerization, using Docker or Kubernetes to deploy applications. Monitoring, integrating with monitoring tools like Prometheus and Grafana. Integration with other CI/CD tools. GitHub integrates with other CI tools such as Jenkins, a widely used CI/CD tool for automating the build process. Travis C, continuous integration for open source projects on GitHub. Circle C, another CI platform used for automating development workflows. Domain 5, project management. This domain covers how GitHub supports project management, allowing teams to track tasks, organize workflows, and collaborate efficiently. Key concepts: GitHub projects. GitHub projects allow you to organize your work using project boards. These are customizable and can be used for tracking tasks and features in a Kanban board, columns for to-do. In progress. Done. Visualizing the progress of a project with cards linked to issues and pull requests. Milestones. Milestones group related issues and pull requests into a single target, often representing a major version or feature. Example, you can create a milestone for v1.0 release and assign all issues and PRs related to this version. Labels. Labels allow you to categorize issues and PRs. Common examples include bug, indicating a problem that needs to be fixed. Enhancement, signaling a feature request. Good first issue, helping new contributors find beginner-friendly tasks. Labels can also be used for priority and status tracking, for example, high priority, blocked. Tracking progress. GitHub provides insights to track a project's health, such as issue resolution time, PR velocity, and code frequency. Use these insights to identify bottlenecks and improve team performance. Domain 6, Privacy, Security, and Administration. This domain emphasizes how to manage privacy, security, and administrative tasks in GitHub, ensuring a safe and efficient working environment. Key concepts. Repository permissions. Collaborators, individual users invited to work on a private repository. They can be given roles such as read, write, or admin access. Teams. In organizations, teams can be created and given specific access to repositories. Public versus private repositories. Public repositories are accessible to everyone, while private repositories are restricted to specific users or teams. Branch protection rules. Enforcing rules on specific branches, for example, main, to ensure that code meets certain criteria before it can be merged. Require status checks, such as tests, to pass before merging. Require code reviews from one or more team members. Prevent forced pushes or deletion of protected branches. Security features. Dependabot, a tool that scans your repository for outdated or insecure dependencies and automatically submits pull requests to update them. Security alerts, notifications about vulnerabilities in your project's dependencies, allowing you to update them promptly. Secret scanning, detects accidental commits of sensitive information like API keys or passwords and alerts you. Secrets management. GitHub allows you to securely store secrets, such as API keys or environment variables, and use them in Actions workflows without exposing them publicly. Audit logs. Organizations can track actions like push events, PR merges, and permission changes using GitHub's audit logs. This is useful for monitoring access and ensuring compliance. Domain 7, Benefits of the GitHub Community. This domain highlights the importance of participating in the GitHub community, contributing to open source projects, and utilizing GitHub's educational and networking resources. Key concepts. Open source contribution. GitHub is home to millions of open source projects. Contributing to open source is a great way to build your portfolio, collaborate with developers from around the world, gain experience with real-world projects. Projects often label issues as good first issue to encourage beginners to get involved. GitHub sponsors. GitHub allows developers to financially support open source maintainers through the GitHub Sponsors program. This enables sustainability for developers working on free software. Discussions. GitHub Discussions is a forum-like feature that allows communities to collaborate on ideas, answer questions, and discuss features or bugs outside the issue tracker. It encourages community engagement without cluttering the issue tracker with non-actionable items. Networking and community engagement. GitHub Universe and other events provide networking opportunities with fellow developers. GitHub provides developer insights, enabling you to showcase your contributions, connect with peers, and find collaborators. GitHub Education. GitHub provides resources and tools for educators and students, such as the GitHub Student Developer Pack, which gives free access to various tools and services for learning purposes. Educational materials, certifications, and learning paths are available for students and professionals alike.